Hello everyone, thank you very much for tuning in, and thank you for the organizers for making this happen despite the cancellation of the physical conference. My talk is concerned with two works, one with journalists Tim Salomon and Human Ohadi that you can find on the archive, and the other one with Matthias Katzful and Human Ohadi that we're presently polishing and that hopefully should be soon in the archive. And the setting for our rigorous result will be as follows. So we assume that omega, a subset of Rd, is a bound domain with Lipschitz boundary, so something like that, a nice domain. And L is an elliptic partial differential operator. So for instance, the Bielaplaschen. And the important part here is that the regularity is such that the solution space is a subset of the continuous functions. So evaluating solutions pointwise makes sense. And then we let G be the Green's function with directly boundary conditions. So essentially the inverse of the differential operator, as you see here to the right. So then we're giving ourselves a bunch of measurement points. So these points xi in omega, such that the biggest radius that doesn't contain any of the xi, the ratio of that to either the smallest distance between two neighboring xi, or an xi in the boundary, such that this is bound above by a constant. And this constant will be sort of implicitly there in all the asymptotic results in this paper. And then we use these points and plug pairs of them into this Green's function to obtain a matrix theta. And for algorithmic purposes, we assume that we know omega, the xi's, and theta, but we don't assume that we know the analytic form of L or G. So why should we care about these things? Well, these thetas are actually quite ubiquitous in applied mathematics. So in computational physics or engineering, oftentimes the physical laws are governed by elliptic partial differential equations, and then G turns out by the solution operator. However, also in fields like Gaussian process statistics, we're interested in these thetas because they are the covariance matrices to use if we want to model our data as a smooth Gaussian process, which is one of the most fundamental types of prior knowledge we can infuse in an estimator. And in a very similar vein, also in kernel methods, we can use these thetas as inner products between points. And again, to express somehow a notion of similarity or relation between data points. And for these applications, we need to perform a number of operations on this theta. So in computational physics, oftentimes we are fine with just computing the matrix vector product, which just means solving the PDE. But in Gaussian process statistics, we are interested in computing the conditional expectation, the conditional covariance, the margin likelihood, its derivatives, and we might want to obtain samples from a Gaussian process with this covariance matrix. The problem for all these applications is that theta is dense. So even storing it takes n square complexity, and performing all these other operations using Cholesky factorization scales cubic in the number of degrees of freedom. And this is a major showstopper for many of these applications if we have either many data points or sort of many degrees of freedom. And so basically the name of the game is now to exploit the structure of the matrix to improve upon this computational complexity. The main code of this talk will be as follows. Part 1, we show that one can actually get the optimal results of this problem by just skipping steps in Gaussian elimination. In part 2, we show that by instead computing Cholesky factors using KL minimization, one can achieve even improve upon this complexity and also get a number of nice algorithmic properties. So the main result of part 1 is as follows. We say that given some accuracy parameter epsilon and knowing only omega and the xi, we will select near linearly many entries of theta and a way to order degrees of freedom. And then from these entries, we will compute a lower triangular matrix that again only has near linear many entries. And now we're claiming that this can be done near linear complexity such that we get an epsilon accurate Cholesky factor of the original matrix. And note in particular that here the complexity only scales logarithmically in the accuracy. Or in other words, we have exponential accuracy of our algorithm. And once we have computed this Cholesky factor, we can use it to approximately evaluate all these other qualities that we were interested in. As byproducts, we will also get a fast solver for elliptic PDE and a sparse approximate PCA. And even though they don't fall strictly into the framework, many popular covariance functions from statistics, like the Matern family of kernels or the Cauchy class, do seem to basically our algorithm does seem to work in practice on them, even though they don't strictly fall into the theoretical framework. So what is this algorithm? And in fact, one nice thing about this algorithm is comparatively simple. And so, as I said, we first want to select a way to order the degrees of freedom. And we do this as follows. At each step, we pick the point that is furthest away from either the point that we've picked so far or the boundary. So first, we might select this x1 here. Then we select the point that's furthest away both from x1 and from the boundary, x2, and so on and so forth. And importantly, at each moment, we store this lk, which is the distance between either the closest point that was picked already or the closest point to the boundary. And that's how we order all the degrees of freedom. Now we want to select the sparsity pattern, because we cannot even compute all the entries of the kernel matrix if we want near linear complexity. So we have to decide which entries to even compute. And we do this as follows. So we are going to construct this pattern column by column. And so the first column corresponds to all the possible interactions of x1 here. And we're going to select only those interactions that are within some tuning parameter rho of this distance to the boundary of x1. So that would make for a relatively dense column. Next, we do the same thing for x2. And again, now because this length scale of x2 is a bit smaller than the one of x1, we will get a slightly sparser column. And we proceed through this algorithm, and we see that consecutive columns become sparser and sparser. And so by a harmonic sum type argument, one can actually show that the resulting number of non-zeros is only near linear. Okay, now we want to compute our Cholesky factor. And to do this, we can use the Cholesky factorization as we've seen here. But the problem is that this is a cubic complexity. We see these 3 for loops over 1 to n. So we propose a small modification, which is often called I = 0 or 0 for incomplete Cholesky factorization, which skips this innermost step whenever only one of these indices is off the sparsity pattern. And as you can imagine, this can greatly improve the complexity. So here on the left, we see the full Cholesky factorization, and we see that it somehow it will also fill in entries that were 0 beforehand, whereas on the right we see this incomplete Cholesky factorization, and that can skip every step that contains sort of black elements of the matrix. And so as it moves to the sparser part of the sparsity pattern, it will become much, much faster than the dense Cholesky factorization. And in fact, one can show that this computation can be done in near linear complexity. Now, why does this work? I mean, we have really done 2 very crude approximations here. We first have set almost all entries to 0, and then we have skipped almost all operations of the Cholesky factorization. So why should this be something good? And we're claiming it actually that these 2 approximations somehow cancel out to an exponentially accurate algorithm. And the reason that it works is that, to begin with, the Cholesky factors in this ordering are sparse. And so here we compare the Cholesky factorization first in the sort of lexicographic ordering, where we go sort of row by row by row. And the resulting factor is, dense. There's no sparsity evident whatsoever. Whereas if we use this maximum ordering here, we see the resulting factor is almost sparse. And this is magnitude on a log 10 scale. So everything remotely blue is essentially 0. But still the question is, why should that be the case? And I don't think this phenomenon is well known, that there are interesting dense matrices actually sparse Cholesky factors. We often think of a Cholesky factorization as something that makes sparse matrices denser. But from a probabilistic point of view, this is actually pretty obvious. So if we look at just a single step of Cholesky factorization, so this is basically this matrix identity, and Cholesky factorization just means recursively applying this matrix identity to this lower right matrix that remains in the middle. if you're well versed with the Gaussian process, you'll see the following, that this guy here is just a conditional expectation, and this guy is a conditional covariance of a Gaussian process with theta as a covariance matrix. Now, this, in some sense, is well known in the sense that these formulae are well known, but this has a very interesting consequence, which is that conditioning of a Gaussian random variable is equivalent to a Gaussian elimination applied to the covariance matrix. In particular, if there's any conditional near independence in the Gaussian process, this is equivalent to having almost sparse Cholesky factors of theta having almost sparse Cholesky factors. So I think this is really shows the power of this point of view, that again, it's hard. There are hardly any examples of dense any examples where people compute sparse Cholesky factors of dense matrices. But on the other hand, it's a very frequent phenomenon in probability that you have a sort of dense correlates the Gaussian process, but after you condition on the right variables, it becomes it decorrelates. And so this tells them there ought to be interesting dense matrices with sparse Cholesky factors. And in fact, one intuition explaining conditional independence in these type of stochastic processes is called the screening effect, which has been studied in spatial statistics. And the idea is pretty simple, that if you have a smooth Gaussian process and you start conditioning on some values, then the correlation length decreases. And so it makes a lot of sense, right? Imagine you have a smooth random process, and I ask you to estimate the value at one point, and I give you the value at a point very close to this point, and then I ask you if you also want to know the value far away. And you would say, oh, the value far away, I don't care. the point close to the target point should give you much more information. And that really expresses the fact that conditional on the point close to the target point should be almost independent of the point far away. And that's exactly the source of this conditional independence. And here we see a simple Matern field, and after conditioning on just 4 degrees of freedom, the correlation length has drastically reduced. And this is really the motivation behind this ordering and sparsity pattern, that after we have conditioned on all the red points here, if the 2 green points are further away from each other than the red points are from each other, then we can expect the green points now to be decorrelated, conditioned on all the red points. And so one can also, as I alluded to at the beginning, one can in fact prove this rigorously, and this uses recent results on operator adaptive wavelets, which again were obtained by applying a probabilistic point of view onto classical numerical linear algebra problems. In this case, how to identify interpolation operators for multi-grid methods. And so I won't have time to go into details here, but these gamlets are somewhat closely related to the Cholesky factors we're computing here. And so by using and extending these type of results, we were able to actually prove the decay of these Cholesky factors. And yes, I have some simple numeric examples. So the first is this, we take some Matern kernels, which up to boundary conditions would fit into this theoretical framework. And we see that maybe for rho, again, rho is this parameter that gives us a trade-off between computation and accuracy. For rho equal to 2, maybe we still see a bit of scatter when plotting the distance between points against the correlation. But once we choose rho equal to 3, we accurately reproduce the original Matern kernel. Same for here for this 3D example. Also some more quantitative results. So first, the near linear scaling of complexity with n, and secondly, we see the exponential decay of the error as we're increasing this tuning parameter of rho. An interesting aspect of this algorithm is that it only ever needs to have access to pairwise distances between points. And still also this ordering and sparsity pattern can be constructed efficiently just using pairwise distance between points, so in near linear complexity. And that means that if the data somehow in a GP regression problem, if the data lies on a low-dimensional manifold in a high-dimensional ambient space, our algorithm can exploit that without even being really aware of this high-dimensional ambient space. And just from a user-friendliness perspective, I think that's a very nice property of this algorithm. So going to the summary, we show that there exists a sparse Cholesky factorization of dense kernel matrices motivated by a probabilistic interpretation of Gaussian elimination. This gives us a fast-track method for both integral and differential operators. We also, I didn't have time to talk about this here, but one can get a good low-rank approximation as a byproduct. And one only needs access to pairwise distance between points and entries of the kernel matrix. So in particular, it's oblivious to the ambit dimension. Now we're going to the part 2, and now the question is what do we maybe not like that much about the algorithm? So we do like that it's a very simple algorithm, few tuning parameters, and it's actually pretty easy to implement a shared memory parallel version of it. And it uses automatically the low intrinsic dimensionality of the dataset. The problem, though, is that the constants are still kind of huge. And in particular, memory is always a concern with these direct methods. The second thing is that distributed implementation is still requires some careful dealing with the communication cost between the different workers. And finally, if we're adding a noise covariance, so we're adding sort of IID noise to the Gaussian process, then this diminishes the screening effect. So here we see we compute the Cholesky factor of a good theta with some added IID noise covariance, and we see as we increase the noise variance, the screening effect almost entirely vanishes. And that's really annoying because, one of the main reasons why we want to include many data points is that we have a lot of noise. But then if we can't apply our algorithm to the setting, it somehow limits its usefulness. So the question is, maybe instead of factorizing theta, so the covariance matrix, maybe it's better to factorize the precision matrix. And in fact, in this same first work, we show that also the Cholesky factor of the precision matrix in the reverse ordering is sparse. In fact, it's even sparser than the Cholesky factor of the covariance matrix. And what's very nice is that this approximation property does not deteriorate when adding multiples of the identity. So here you see on the top, you see the Cholesky factor of the covariance matrix, and you see the decay of the screening effect as we're adding a noise. Whereas on the bottom, we see that there's no difference over the different sigmas that we're adding to the precision matrix. And now there's a simple algebraic trick where we can write the theta plus identity as theta times theta inverse plus identity. And this way we can apply the Cholesky factorization to this and to this separately and get an accurate approximation, because these terms will always be subject to a good screening effect. Now the question is, how do we compute this? Like we cannot use Gaussian elimination because we have access only to entries of theta, and we want to compute Cholesky factors of its inverse. So one can actually write down a similar recursive procedure to compute the sort of inverse Cholesky factorization in this very nice complexity n times log to the 2d 1 of epsilon. However, and I spent about a month of my life trying to make this work, it doesn't work in practice. It's extremely unstable. And I think basically the problem is that somehow the bad condition number of the matrix inverse is hitting the computation and leads to a immense sort of snowballing of the computational error. So that really doesn't work in practice. So the question is, like, is there other ways? Are there other ways to do it? And again, this will be sort of a bit probability to the rescue, because in recent work by Yusuf Mazuk and his group at MIT, they were using these nonlinear transfer maps a lot, where they say they want to sample from a certain complicated Gaussian, not Gaussian process, and the way they do is they compute a transfer map that maps a IID Gaussian to this complicated distribution. And really, if we say basically the Cholesky factor of the covariance is just a transfer map that maps an IID Gaussian to a Gaussian with a given covariance. So we could think, maybe we can also use these variational methods for to compute our Cholesky factors. But the problem is that, or at least for a while, I thought the problem is that this would be too slow for fast linear algebra, because you have this non-quadratic optimization problem. And in linear algebra, the competition is really on its toes, so the competition is tough. But it turns out that there's something very, very nice happening. So if we actually do this, so we now compute we want to find an inverse Cholesky factor L such that minimize the distance between in KL between the original process and the process implied by this L if we interpret it as the Cholesky factor of the inverse covariance of the precision matrix. Now then we can just do a bit of massaging. So there exists a closed form of this K divergent, which is given here. Then we can drop these terms because they don't depend on L. We're left with that. And we also use the cyclic property of this trace. And now we can rewrite the problem as such. And we see that this problem entirely decouples over this sum of terms here that only depend on one column of L at a time. And in particular, for this particular problem, we can write down the optimality conditions and we can find out that actually there exists a closed form solution of each column of this KL minimizer. And so that means that we can just compute all these columns in parallel without any communication among them and get our KL minimizing inverse factor this way. And this sort of update rule, in fact, has been discovered in 3 different communities independently of each other. So probably historically, the first is in spatial statistics, the so-called Vecchi approximation. However, there was no real optimality properties known about this Vecchi approximation. Then in this approximate inverse community, it was known to be the minimizer of the Caprin condition number or of this fidelity term with a diagonal constraint. And finally, then this ongoing work on transferred maps by Mazuk et al. These properties have also been used again in this more general case of wanting to map Gaussians, ID Gaussians to arbitrary stochastic processes. One a bit annoying thing is that still the computational complexity is n times rho to the 3D. We would like it to be n times rho to the 2D, which would be in line with the incomplete Cholesky factorization. And to this end, what one can do is one can observe that many of these columns will almost have the same, will sort of almost be subset of each other. So we can just add a few entries to these columns and make them subsets of each other. And this means that this complexity comes from the fact that we need to compute a Cholesky factorization for every column. But if some columns are subsets of each other, we can actually compute one Cholesky factorization for the biggest column and use it to update all of these 3 columns. And by doing a sort of a aggregation scheme like that, where we have like many nearby points that all have their own sort of set of points to interact with, and instead we say all these points interact with all these points in here interact with all these points, we can actually reduce the computational complexity to n times rho to the 2D, which, as far as I know, is the best complexity for these type of problems. Another nice thing about this algorithm is that since we're computing only the inverse Cholesky factor, we actually don't need to really store it. We can, if we're doing Gaussian process regression, we can just directly apply it to the data as we're computing it and then forget about it. And by doing this 2 times, we can compute our posterior mean. So in fact, the memory complexity is just n plus rho to the 2D. And what's also nice is we can send all these columns to the different workers. And so for basically communicating rho to the 2D flops to a worker, this worker can then do rho to the 3D flops in pretty standard linear algebra operations, and then again communicate a simple result back. So it's very friendly to distributed computation. In summary, the asymptotic complexity turns out to be, and I haven't talked about the algorithm here, but they're in the papers, n log n for the ordering. Then again, the sparse dependent can be done n log n, and we can perform GP regression in the slightly higher complexity, but is embarrassingly parallel. So these are, I think, computationally very attractive properties. And so the overall space complexity is of the order n plus the number of workers times rho to the d. In practice, there's an important point that it's crucial to include the prediction points into the approximation. So we don't want to just apply the prediction to the training covariance and use it to invert it, but we want to apply this sort of approximation to the joint training and prediction covariance. And this again is motivated by this variational property, which ensures that some of this optimality falls onto the entire process, and that greatly increase the stability for small values of rho. And so for some numeric examples, so here we see basically the problem where we're adding this identity to a Matern covariance, and we see that and there are a number of like small variations of these schemes to compute with a nugget by using the fact that we now have access to the inverse covariance. And we see that, at least for if we use a slightly bigger sparsity pattern here, we see that we basically keep improving our approximation as we both either increase sigma or increase rho. Whereas the naive approximation deteriorates drastically in both cases when we have to deal with a sigma. The second example in spatial statistics. So here we generated 1 million points on a square using the FFT, and then do basically spatial statistics with it. So we try to predict the values either of these red points or these orange points, and we see that once we reach like a row of the order 4, both the accuracy of the posterior mean as a predictor and also the coverage of the 90% confidence interval converges towards the right value, essentially. And now we also see that when we use this aggregation scheme, we do indeed drastically improve the asymptotic complexity, so particularly the scaling as we're increasing rho, as our theory predicts. And just to give you some idea of the timings, if we are using rho equal to 4, which in the example just before gave us a good accuracy, then we just take 10 seconds to invert a matrix of 1 million times 1 million, up to the accuracy that is needed by the problem. So I think that those are, in terms of pure sort of numbers, are pretty nice results. And another example that we've been trying is boundary element methods. So really, through the Gaussian process perspective, a single layer boundary element method is just we compute the conditional expectation of a Gaussian process subject to measurements on the boundary of the domain. And again, we see that even for these very small values of rho equal to 1 or 2, we can get almost discretization accuracy in these examples. And I mean, this is still to be tested further, but we think these are very encouraging results. And so in summary, we show that introducing this KL minimization leads to state-of-the-art computational complexity, and to many very nice properties like this embarrassing parallelism, the linear space complexity, and the stability in the low accuracy regime. They're not really present in classical multiscale algorithms for this problem. And we think also that this is a possible candidate for a user-friendly tool to do GP regression on large data sets. And that's also what we're going to push further. Well, thank you very much. And yeah, I hope you have a good day.